Yeah, thanks on everyone. Let's start off. The last class we have doing surface tension. This was the last problem that we did. We have taken two parallel plates and the liquid was rising between them because of the surface tension there. Hope everyone has gone through the notes. Great. Let's see a question based on this. So there, this was the question. If you look at this, we had two parallel plates, right? And the surface, right, was like a cylindrical thing. It's like that stretcher. When you put a patient on a stretcher, that is how the surface is like that. And that two SL ka components, SL cos theta are balancing mg, and that is how we found it. What if instead of keeping them parallel, what if you keep them at an angle? So the surface is something like this. The angle between them is alpha. And when you keep this thing on a liquid, the liquid actually rises. Look at this equation. If you remember, the h is proportional to 1 by d. So d is the distance between the plates. So more the distance between the plates, lesser the height. So this liquid is actually going to become something of this sort. So you won't get a cylinder there, you will get some curve. Let this length be L. Right, and this is your surface. S is the surface tension. Theta is the contact angle. Two plates joined at one side. And then making an angle alpha between them. So here on the edge, these two things, right? It's like you folded a plate by an angle alpha. Right? So this is placed on a liquid surface. And the liquid level rises differently at different spots. I want you to find the equation of this liquid surface. Basically, I want you to find the surface of this edge basically. You can choose one side as x-axis and the origin as that corner, and you can do it. And for simplicity now, take this as x-axis. This is origin and this is y-axis. So I want you to find the equation of that line there. I hope the question is clear. We proved it in the last thing. The more the distance, lesser the height. So as the distance between them is increasing, the height will keep decreasing. So you'll get a curve. How do you find the shape of that curve? Anyone not clear with the picture, please ask me. Hmm. Density of the liquid is rho. You can take all that stuff. It looks a little scary and weird, but it's solvable. But did you guys get the picture how it is? It's like if you look into my screen, right? These are the two plates. If you can see both my hands, they're open like this. Able to visualize? They're opening like this. Basically, if these are the two plates, they're completely zero. They opened up like this, and you place them on the water surface. So again, same thing. You need to ask yourself, why is the liquid rising? So if you start from there, you will notice it. See, at a distance x from here, take a small dx. So let's take a small dx here. This piece, I'm taking that small piece there. So this is the dx. If that is x, then this length will be x alpha. That is your arc length, isn't it? If that is alpha, then this length here will be x alpha. This is your y ka height. Now, if you look at the surface tension force, it is actually acting like this. And if you look at this is your angle theta. So that is your vertical components there. So how much will that force be? This will be s into dx. This will be s into dx. And your own weight, mg, is acting downward. So we are taking about a small cross section there. Right, we are ignoring these two forces because they're almost the same length. Remember, dx is very, very small. So this thing and this thing. So basically, it is the forces coming because of touching the solid there. So this would be how much? 2 s dx cos theta is balancing the weight of that small piece mg. Mg will be how much? So you can take that like a small cylinder there, which is density of the liquid. Dx is the width, x alpha, height is y. length, breadth, height into g. Dx goes off. You end up with x into y is equal to 2s cos theta by rho g alpha. 2 is constant, s is constant, theta is constant, rho is constant, g is and alpha is constant. So this is constant. This is a rectangular hyperbola. PV is equal to constant, remember? So that shape which you get is a hyperbola. हाँ आ
Sir, how will we get cos theta?
Because ये contact angle है ना. Contact angle is what? यहाँ पे cos theta कैसा आया?
Okay, right, it's contact angle. Sorry.
Alpha नहीं है. Alpha is different. Basically, I did the same question, but we took a very small piece. All clear with this? If you see this and the previous question are exactly same, this thing looks more scary, but isn't that what I did? I took a small piece, SL cos theta is equal to MGC, same thing I wrote. The only thing is the L ka place mein we got dx. Got this? That's a good one, not a tough one, but a decent one. So now let's see something good. An advanced paragraph level question. Look at this. So we have a pipe here. Right side we have a big pipe and left side we have a small pipe. Then what you did, you started dropping water drop by drop. Since the radius is big, you can neglect the capillary action here. Remember, capillary action is pretty strong when the radius is small. So neglect the capillary effect on the right side, but right on the left hand side, you can treat it like a capillary, thin pipe. And you started pouring liquid drop by drop, and something happens here. For some reason, the height on both the sides is not same. This height is h1, and this height is h2. And why the height is not same? We have done a problem like that. If you remember here, yeah, the equation. If you take r1 and r2, the height, the difference in height is this. If you include capillary action, the height on both the limbs will not be same. It will depend on the radius. So here one limb is pretty large and one limb is pretty small. So you're dropping the water regularly, drop by drop, slowly. Plot H1 and H2 versus time graph. This is a pretty good one. Matlab the whole analysis is a pretty good thing. Try. Approximately how will the graph look like? You need to put it. There are a lot of questions you can ask on this, like what is the maximum height on that? What happens here? What is that? A lot of things. Try. Think 2-3 minutes. Let's see. Yeah.
Sir, H1 is the height of the capillary or the height of the water level?
Height of the water, height of the capillary नहीं है.
Sir,
I drawn a
because
picture में देखो ना.
in the question first line they have said capillary tube of height H1.
I ignore कर लेना. What doesn't matter.
Okay, sir.
बस H ले लेना. See, forget about drawing the graph. Forget about that. Take 2 minutes, think what is happening. When you pour the liquid, what happens? Then what happens? Then what happens? Why that happened? Ask yourself questions. Take 2 3 minutes, think about that. There's no point in jumping into the question even before understanding what is happening. Hmm, let's see. So let's put the picture there and see what happens. Let's understand the whole scenario before even jumping into the graph. ठीक है. First thing, you started pouring the liquid drop by drop, right? Now, what happens? The moment you drop, remember the surface tension will pull it, all the liquid will start going into the capillary, right? All the liquid will go into the capillary because the capillary action is there, which is pulling 2s cos theta, 2 pi r s cos theta. That will pull all the water up. All liquid goes into capillary. In this thing, there will be no liquid. So the height h1 is increasing. Great. This will happen till when? This will happen till you reach that optimal height where h is equal to 2s cos theta by rho gr. If you remember, this is the formula we derived for height of the capillary. So till this point, the water will keep rising, right? And this would be the height there. Let's call this thing h. And h2 is 0. And h1 will become equal to h. Now, after this point, once you start putting the water, now what will happen? Now, because see, this much height the capillary will pull anyway. Now, whatever water that you're adding, now this is just because of the pressure. The liquid on the right side will start rising, H2. Now, on top of H2, you'll get that extra height H. So this liquid which you will get here, This would be that additional height, which is 2SR, 2S cos theta by rho GR. This will be the new height H1. That means the height of the liquid on the right side will start increasing once you cross this minimum level of 2S cos theta by rho GR. So far clear? So initially when you put little water, the surface tension will dominate, all the water will get sucked in by the capillary. The 2 pi rs cos theta will pull it up. It will keep on absorbing the liquid, it will keep on absorbing the liquid till it reaches this height 2S cos theta rho GR. After this point, the 2 pi rs cos theta becomes equal to mg, it cannot pull the water more. Then whatever additional water is coming, we are ignoring the size of this pipe here, right? Neglect the volume of the connecting pipe. So then the water starts accumulating on the right hand side. Now if the water accumulates on the right hand side, now because of fluid mechanics, we saw pressure, the heights will be same, plus additional 2 pi rs cos theta, that mg thing will come back. So here, if you look at the height difference here, H2, H1 minus H2 will be 2S cos theta by rho GR. So this is the ratio they will maintain, or this difference they will maintain. Till when? Now this height will keep on going, it will completely fill the tube. So here also you'll reach a certain height. Great. Now what happens? Now if you start putting more liquid, you will not get a fountain. Remember this question which we did? If the boat has a small hole and if you push the boat inside, do you get a fountain inside? First you get a small bubble, right? Like a blood car drop, like this. You'll get a small drop. Once you put enough pressure, it pops and then it goes off. So the water will not come out immediately. It actually forms a small bubble. You start getting a small bulge here. The liquid bulges. Like this. There, I think now this picture makes sense. Can you see that bulge? So this was actually connected to that pipe. You get a bulge like this. So you won't get a fountain immediately. So that means the water on the right side is still increasing. It goes beyond the hole actually. This height will be h dash. And how do we calculate that? So outside the pressure is P naught. Pressure just inside, we know P naught plus 2S by small r. And so P naught plus 2S by r. This is just like that whole question, P naught plus rho g h dash. That means height on the right side will keep increasing till you reach 2S by rho g r. So once you reach that height, then the water starts leaking. That is a maximum height you can reach on the other side. Once you cross this level, the bubble will pop and the liquid will start coming out. It starts leaking from the edges. So basically on the left hand side, H1 becomes constant. And on the right hand side also, H2 becomes constant. So whatever liquid you're pouring, that starts leaking out. So whatever liquid comes in will start leaking out and H2 becomes constant. So your final H2 so this was H2, this was H1, and this difference here, so this additional height to pop the liquid is your H dash, which is 2S by rho GR. At this point, you're done. Whatever liquid is going on, everything is coming out. Question is, this is the whole picture that is happening. Please have a look at the whole thing, what is happening. Step 1, all the liquid will get pulled into the capillary. Step 2, once the capillary is full, then the liquid starts accumulating on the right hand side, on the left hand side. Now both of them will rise at the same level. So whatever is H2 increasing, the same way H1 is increasing. Now see, H1, H2 are not equal, but the rate of change of height is equal. Then H1 will be completely full. Then H2 will start increasing and it will not overflow when the height becomes same. The height has to exceed the initial height so that you get a bulge. So this bulge is not pulling anymore, now it is actually pushing the liquid inside. And that bulge will pop when the height is 2s by rho gr. Once you exceed this h2, h dash, the water will start coming out. So you're done with the question. Please have a look at this whole page. Now we have to draw the graph. That's a different thing. But first, the understanding thing. All clear with this? Anything. Matlab, I will number them if you want. This is like state 1, state 2, state 3, state 4, state 5, and state 6. Any state that you're not convinced. Now, then let's see the graph. So initially, both the heights are 0. I'll use the red one. So the h1 will initially increase, increase, increase. So this is the point where 2s cos theta by rho gr. The left side capillary will reach maximum. This is your h1. During this time, what is h2 doing? I'm drawing it in green. h2 is doing nothing. h2 is 0. After this, what will happen? Both of them will increase at the same rate. So yeah, it will be increasing little slowly. The h2 is also increasing slowly. If you see, the difference will remain constant. Both are increasing at the same rate. This will happen till when? So rate of change of h1 and h2, meaning the slopes are same. So if I have to number the stages now, this is stage 1. This entire thing you're going from stage 1 to 2. So this is that stage 1 to 2 ka transition. This thing is a 2 to 3 ka transition. So basically you will be full actually 2 to 4 transition, but I think that will be confusing to write. And then what will happen? H1, right? You have reached the top, you're done. This is your H1. So basically at this point, the liquid reaches the top. After this, what happens? Now, whatever liquid you're pouring, all the liquid will go into the right side. The left side will not take any more liquid. It is just forming a bulge. So the green one will increase, but slightly it will change slightly. There will be a slight change. So rate of change slightly increases because all the liquid goes into the right side now. Previously, whatever liquid you're giving was shaded by the left and right. Yeah, but it'll be very slight change because it's a very small thing.
Sir, will the
So, right.
slope become as same as the first wala change, like the
नहीं ना
initial part
एरिया
of the?
एरिया अलग है ना रे गॉड वॉल्यूम रेट इज सेम एरियाज आर डिफरेंट ना एक्चुअली वो स्लोप बहुत छोटा होगा ठीक है and then what will happen, this will just keep on increasing, 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 and then this becomes constant. So this h2 will actually exceed h1. So this is the point where the liquid starts leaking. Straight line, but liquid starts leaking. So previously the height will, the rate, right? Again, if you look at here, the rate will start decreasing. The rate of change of height will decrease because the liquid is shaded by both of them now. Again, all straight lines are no curves and all, but the slopes will keep changing a bit. So here I can put more data here at any point of time. If you look at the difference between them, this difference will be always 2s cos theta by rho gr. If you look at the difference between these two, this will be 2s by rho g small r. This is when the bubble pops. This is your h dash. Basically, this calculation which we did. Please have a look at the graph. Is the graph making sense, everyone? So initially h1 will increase, then it will increase, but little slowly and then becomes constant. Once you get the top, you can't increase anymore. H1 has a fixed value. But for H2, initially it will do nothing. Then it will increase with H1. Then H1 will stop increasing. So all the liquid will go to H2. So it will increase little faster. It will keep increasing, keep increasing. They reach the same height. Getting it up to this point, you won't get a bulge. So this is the point where the bulge forms actually. This point is the thing where the bulge starts appearing. Bulge appears on capillary. Till here, the bulge won't be there. That is a point where the bulge appears. And this is where that bulge will pop. And once the bubble pops, you're done. This is a graph between the time and versus the heights. Clear with this? Yeah, it's a pretty good question. Again, if you see it is, you have to analyze and you have to observe there. Yeah.
Sir, so like the entire time the red thing is constant till the liquid
Hmm.
leaks, uh,
Yeah.
the water is been filled in a sphere, like the bulge wala sphere.
हाँ मतलब स्पीयर मतलब बहुत छोटा है ना वो नेग्लिजिबल वॉल्यूम है
Huh. So,
बट
so the
बट
graph should
मोस्ट
be
ऑफ
a little
द
bit more compressed.
हाँ बट ठीक है मतलब वो आर बहुत छोटा है ऑलरेडी उसमें अगेन यू टेकिंग अ स्मॉल हेमिस्फीयर तो
Hmm.
इट्स
Okay, sir.
फाइन गॉट दिस एवरीवन pretty good question. I should definitely try this on your own again.
So this happens very quickly, right? H2 and H1 are there is a very little gap, right?
H2 and
H1, the maximum ones.
ये बोल रहे हो
Yes, this gap will be very little,
that
right?
will be very small. Actually, surface tension बहुत छोटा है ना. That will be like depends again at what rate are you putting the liquid na. If you're putting little fast, the time will be small. If you're putting really slow, 1 ml, 1 ml, 1 ml, then you can actually extend the time. So graph will look like this. Exact times तो पता नहीं. All clear with this? That's a pretty good question. You should definitely try. So there, with that, we are done with surface tension. Again, like I said, it's a small chapter. Like viscosity, surface tension, elasticity. Combined is one chapter called properties of matter. Right? We are doing it separately because, and like I said, surface tension, right? If you see, there primarily there are only two concepts. One was the surface tension force, SL, surface energy, and capillary action. So there, we did a good amount of varieties. So please make sure to resolve them. Chapter is not tough, but people, it can get little confusing because of that surfaces and all that stuff. So please do try to solve as soon as you can. I'll send you a sheet also on viscosity and surface tension. The next thing is elasticity. Again, this is also a very small chapter. Mostly we might wrap it up by next class because there are few questions based on heat and thermodynamics. So that will be the next chapter. So we're going to do it there. So what is elasticity? So the most common misconception, right? When you hear the word elastic, people think of rubber, right? I think I'll start with a small simple question. This question came in CET. Which is more elastic, steel or rubber? This was a question in CET exam. Which is more elastic, steel or rubber? Right? We think it is rubber, right? Now you need to understand. So the thing, you know what? The problem is people have misused that word. It is like, I still remember when we were in school now, we used to say, teacher, I need to go to toilet. Then somewhere down the line that became, washroom. Then it became restroom, right? Now it looks more posh, right? Now in restroom, you actually don't go and rest. In washroom, you don't wash anything, right? So somewhere down the line, people started thinking elastic matlab stretchability. So what is the meaning of elastic? We'll see. So elasticity simply means, right? It is actually tells you how difficult it is to deform a body. But yeah, let's go to the fundamental word. So first of all, why do you get forces? Like whenever you take a body, when you try to stretch or compress, why do you get forces? Why does it resist? So we need to go to the fundamental at the molecular level. So if you consider two molecules in a lattice, force between molecules, this is what actually happens. So let's say if you have a nucleus, so even though we say the atom is neutral, the electrons are randomly distributed. So all the charge is not single place like a nucleus. But because of this, what will happen? So let's call this thing molecule 2, molecule 1. So the nucleus of molecule 1 attracts electrons of molecule 2, right? And vice versa. Yeah, on top of it, you also have that covalent bond, ionic bond, all that bonding stuff. So we'll not get into that, right? So this force is attractive in nature because we know unlike charges attract. Great. But what if you push them a little closer? If molecules are pushed a little closer, they start attracting. But what if you push even further? And if you push more, at some point, the nucleus repulsion starts becoming dominating because the nucleus is concentrated charge. So that force which is attractive suddenly starts becoming repulsive. So that means up to a certain point, they'll form a bond, but if you try to push them too much, they'll start repelling. And force becomes repulsive. That is the reason you cannot combine two different nucleuses to create a new element automatically. You need really a lot of energy. That's what we call as nuclear fusion. So if you try to plot this on a graph, so if you plot a graph between the force versus the R is the distance between the molecules. The graph would look something like this. So look at this graph. If R is very, very large, if R is infinity, the forces are zero. This is slightly attractive, but force is zero. If you bring them closer, meaning R is decreasing, the force is becoming more and more negative. Negative force indicates attraction. The negative force indicates attraction. So if you keep pushing them, at some point you get a maximum force. This is your R naught, right? This is the point where your force becomes zero. This is R1. And if you keep pushing further, the force becomes repulsive. Right? And if you try to plot a potential energy graph for this, U versus R graph, hope you remember F is equal to minus du by dr. So the position where the slope is zero, that is your force. So that means in this thing, this would be the graph. So here the graph would be the minimum will occur here. The graph would look something like this. So there. So this position is the point where your energy is minimum, and that's what we call as bond length. Making sense? So every system will try to achieve a state of least energy. So when you put two molecules, they will try to come to a distance where the attraction force is like, you can say, the energy is minimum. So if you have only two atoms, right, they will have a maximum attraction force. But we have molecules in a lattice. But is the story clear? Just a basic idea. Let's not go too deep into it. Chemistry, there is more, but this gives you a rough idea what is happening. So when you keep two molecules far, they'll attract. When you keep them too close, they'll repel. That is our main thing. So there's a particular distance they want to be. If you change that distance, they're not happy about it. Now, when you keep molecules in a lattice, now you don't have a single molecule. You're surrounded by multiple molecules. Now everyone is attracting you with a force in all directions. So F net is zero. Now, for some reason, if you try to displace the molecule, and you brought like this, like you brought this guy closer here. So if you bring him closer, what will happen? This guy will repel. And these people, because you went away far from them, they will attract. Can you see what will happen? It will try to push back. So the net force will be towards the mean position. Mean position is the point where the force is zero. There. So fundamentally, this is what is happening. That is the reason when you take a body, whether you try to compress it or whether you try to expand it, in both the cases, it will fight back with you. A body does not want to compress, a body does not want to elongate. Because if you try to elongate, molecular distance will increase, they'll pull you back again. Look at this position here. If you look at the force ka graph, this is the position there. You try to increase the distance, the force will decrease, it'll try to come back. You increase the distance, it'll try to come back. Basically, it's like a stable equilibrium, isn't it? It'll always try to come back to that position. Are you guys able to connect it with that equilibrium thing in work power energy? Any doubts on the story so far? So just get that context there, what is happening. So if you are far, you'll attract. If you get too close, you will repel. So there's a particular point they want to be, right? So when a body is deformed, so when I say deformed, elongation or compression, right? Internal restoring forces are generated. That is a technical name. Look at the word internal. These forces are inside. Restoring, they're trying to bring you back to the natural state. That's why they're called restoring forces. But again, nothing, it's just a fancy word. This is nothing but tension in the rod. This is the force which you call as tension in the rod, tension in the string, tension in the spring. It is that only. So internal restoring forces are nothing new. You already know about them. So these forces are generated. And what is the job of these things? They try to bring, they will, which try to bring the body. They try, okay? Every time they might not be successful. They try to bring the body to the natural state. This property of resisting deformation is called elasticity. So now if someone asks you what is elasticity, so elasticity is not stretching. Elasticity tells you like how much are you fighting back? Like if I deform you, how much are you resisting? So now if I ask the same question, right, which is more elastic? steel or rubber. Think of like this. If you stretch a rubber sheet by 10 centimeter and a steel wire by 10 centimeter, which is more difficult? A steel wire is more difficult, isn't it? So steel is more elastic than rubber. So the word was being misused. You should say rubber is more stretchable. But somewhere down the line, elastic matlab, people started thinking it will stretch more. So elastic band, completely wrong word, but yeah, which is more elastic, steel or rubber. So steel is more difficult to deform. Rubber is more stretchable. Yeah. Yeah, it is non-linear, but for small deformations, we can take it as linear. All clear so far? There, this is the intro part. Like, why do you get forces in the first place? So you should have an idea why you get forces. Next thing, if you remember, we did discuss on this a bit somewhere, where in center of mass, plastic body. So plastic body is the opposite of that. So what is the plastic body? So quotient restitution E is zero. If you remember, na center of mass mein we had this discussion in collisions. I told you, elastic body does not mean, it will not deform or something. It will deform there. What is an elastic body? These bodies deform when force is applied, but they completely recover. So don't get confused between a rigid body and an elastic body. Rigid body will not deform in the first place. No matter how much force you apply, it will not deform. So plastic body, coefficient of restitution is zero. So these things do not generate any internal restoring forces. Chapati down. You stretch them, it will just stay back, it just stays there. It does not try to go back at all. Perfect. Now there are a few terminologies there you should know. When someone says the material is brittle, means what? This will easily break. They're difficult to stretch. They can be stronger. We'll talk about that. They're difficult to stretch and they'll crack. Example glass. So, how to break a glass or something. This old bulbs used to be there. Did you guys see this movie Dangal? You must have seen it. In that, there's a scene. Every day morning, his dad takes her, to the her practice and everything. So one day she gets pissed off, and the bulb which is there, she puts water on the bulb. Do you remember that scene? The bulb goes off. Do you remember there's a scene in the movie like that? So what actually happens when you have a bulb, right? Because of the heat, it gets really heated up. All you need to do is put a little water droplet here. So what will happen? This part will cool down. So it will try to contract. But this part which is heated will try to expand. The glass will break. Just put some water on a bulb. So switch on the bulb for 5 minutes. Once it gets hot, put a water. It will automatically, the glass will break. Bulb is gone. That's what happens actually in the movie. Now, India may it doesn't happen, but when you go to these cold countries, right, they have this problem. The entire car ka glass, right, becomes ice. So what some people do, they take hot water, they boil some hot water and try to put it on the glass to melt that ice. The most nonsense thing you can do. The moment the hot water touches that glass, that part will start expanding because it is getting heated up. The surrounding is getting contracting. The glass will develop stress and the whole glass will break. So actually, you can do this. If you want to break your neighbor ka car ka glass, you can take some liquid nitrogen and 100 degrees hot water. First pour liquid nitrogen on the glass, wait for a minute, and then pour hot water. The glass will crack. Right? Yeah, but liquid nitrogen or something cold. So you need the entire ice to form there. So yeah, works. So these materials are brittle. Then you hear words like ductile. So there is a movie also, right? In that they try to rob a bank. So what they do, they take liquid nitrogen and the entire vault is made of steel. So the hinges which are there made of steel, they put liquid nitrogen. So what will happen? The hinges are made of steel, right? They try to contract, but the surrounding concrete will not contract. So once this thing tries to contract, right, the bolts become loose. Then you just have to take a hammer and beat them right and left, and they crack. The safe opens. I'm not sure how that works, but movie method works. You need to have enough liquid nitrogen to pour and wait so that no one comes. So yeah. Now what is the ductile? They can be stretched easily, and you can make them into wires. A copper is a pretty good example. Then you sometimes you'll hear the word called malleability. I'm sure you must have heard these words in chemistry. This is they can be made into thin sheets, gold. If you take a 1 gram gold, you can make it as thin as, you can make a sheet as big as the size of your room you're sitting right now. You can make it really, really thin. You must have heard that, na? They put this gold ka wafer, on top of sweets. Nowadays it become too expensive, but you must have seen some sweets like that. I think normally they put silver. That has also become expensive. Thin sheets, example gold. So did you guys ever think about it? Why Rutherford used gold in the Rutherford gold foil experiment? Because he is rich. They had a lot of gold. So he thought I'll use gold. He's Batman, something like that. So why do you think he used gold? Kabhi socha? Because the gold, right? Yeah, you can minimize it. You can take gold and you can hammer it into a very thin sheet, almost to a size of a micron, 10 power minus 6 meters we're talking about. Right. So because see, if the sheet is very thin, the alpha particles will have less resistance. They can actually go through them. So yeah, theoretically you can make it very thin. Anyway, so that is one part of it. Now this chapter is, yeah, gold foils can be very thin. This chapter is very important if you're taking tomorrow mechanical or civil engineering. Because when you talk about strength of a material, there are different kinds of strengths we talk about, right? So all the things are not same. So let's see what are these things exactly. So if you consider a body in equilibrium, acted upon by forces. So let's say we have some random body there, and let's say we have forces F1, F2, F3, and F4. If you draw an FBD by cutting in half, and if you take any one piece, and if you look at the forces here, F3 and F4, you will realize that this cross section, there are two forces actually. There is a force ka component which is perpendicular to the surface, and there's a force ka component which is parallel to the surface. Basically, this is your tension. The net tension is at an angle, but this force will have two components there. So we define something called longitudinal stress. Which is the force perpendicular by area of cross section. Then we define something called shearing stress, which is the force parallel by area of cross section. Right? And there's a third thing called volume stress. We'll talk about stress exactly. What is stress there? Why we need to define it. So volume stress, this is for 3D things. So when you have an object there and it is being compressed in all directions. So volume stress is this the force perpendicular to the surface area. This is what we studied in fluid mechanics as pressure. So be careful, the previous two things are not pressure. These are not pressures. This is area of cross section. Pressure is surface area. Just because you saw force by area, don't think it is pressure. So what is this exactly then? What is stress exactly? This is not pressure. So let me ask you this question. Let's say tomorrow you're studying some structures, or let's say you're a biologist. If I ask you this question, are the bones of an elephant stronger or bones of a rat stronger? Are the bones of an elephant stronger or bones of a rat stronger? How do you compare them? Now, if you say elephant, just because the bones are thicker, you're doing something wrong. So let me ask you this way. Is a plastic stronger or steel stronger?
Mm.
So again, you have to ask something here. If you take even a normal plastic, right? What if I take a plastic pipe, which is 1 meter wide, and what if I take a steel wire of only 1 mm? Do you still think the steel is stronger? You're getting the problem there. You're not actually comparing them one is to one. So how do you say when two things are strong? You compare them with something same, right? Let me ask you like this thing. I have 10 oranges are more expensive than one apple. Therefore, oranges are expensive. What do you think about the statement? 10 oranges are more expensive than one apple. Therefore, oranges are greater than expensive than apple. You're getting the problem there? The comparison is wrong. You compare one apple to one orange, and then maybe you can talk, or even that comparison is wrong. What if you took a super hybrid apple, which is this big, and you took a dwarf orange, and that is this small? Maybe you'll compare 1 kg apples to 1 kg oranges. So same way, so tomorrow when you're a mechanical engineer and if you're constructing a pillar, what you want is not the force. What you're more interested is for a given area, how much force can you withstand? So when you compare rat and elephant ka bones, what are you supposed to do? You actually do this thing. Matlab, if the rat is the same size as an elephant, then you can compare the bones, right? So getting it directly comparing, obviously elephant ka bone is definitely stronger than a rat, but that's a wrong comparison. So what we do, we take the rat ka bone, right, and we measure the area. Let's say it is 1 millimeter square or 1 centimeter square, and then we try to apply some force slowly, and we see at what point it will crack. And for example, let's say it can withstand 100 newtons and 1 centimeter square it cracks. So that thing comes out to be 100, and 10 centimeter square is 10 power minus 4. That's around 10 power 6 Newton per meter square. The same thing when you do for a elephant ka bone, maybe elephant ka bone is thicker, let's say 50 centimeter square or maybe 100 centimeter square. And let's say elephant ka bone rate cracks at 2000 kgs. So that's around 20,000 tons. That would be 100 into 10 power minus 4. So 0 goes off. That will be 2 into 10 power 6. Now the comparison makes sense, isn't it? Now you can say the elephant ka bones are 2 times stronger than the rat ka bones. Are you getting the comparison? But let's say this rat ka bone could actually withstand, let's say 400 or 600. That would be 6 into 10 power 6. So that now you say rat ka things are actually stronger, 3 times stronger. But now, if you're a biologist, right, you will understand one thing. Generally, bones are made of calcium and whatever compound. So, generally, shouldn't all of them get the same ratio? Whether you make a rat or a elephant or a human, and if the bone ka composition is same, the strength should be almost same, isn't it? But for some reason, you actually notice the rat ka bones are stronger, 3 times stronger. Then you know there is some issue with the composition. Then you actually go and study the composition of the rat ka bone, and you notice there's actually more calcium in the catga bone, and you will figure out things like that. There are certain humans, they have an abnormality in one of the genes. This is a very few percentage. Their bones are 3 times denser than normal human beings. These people never get fractures. Ever heard about it? There's a very few percentage of the population they have. These people have a very difficult swimming also because their bones are denser. Or did you ever hear this word when there is someone really fat and when the weight is too much, they say bone weight? This too, you must have heard it. Instead of saying I'm fat, they simply say my bone weight is more. So there are a few people like that. I knew one guy in my school. That guy got bones, right? Matlab, he had something. He fell from a first floor or something. Nothing happened. He just got up and just walked away. Their bones are pretty dense, right? So normally people get fractures and stuff, but that is there. So the composition can be different. So if you're a biologist, right, based on that thing, you can study. So tomorrow, if you're a mechanical engineer or a civil guy and you're working on materials, you're not interested in force. That's a very bad thing to study. You are actually interested in force per unit area. You're getting it? So comparing force doesn't make sense. So we'll talk about that. Take a break. Come back by 9:40. We'll continue from here. Sure, let's start off. Sure, comes on everyone. So we have three kinds of stresses: longitudinal stress, shearing stress, and volume stress. So what are these exactly? Again, when you're doing construction, right, or anything, it is important that you know what kind of stress you're dealing with. For example, if you take a paper, right, and if you try to stretch a paper, so this is your cross section area. So if you try to pull a paper, right, so stretching a paper is the longitudinal stress. Comes on everyone. But tell me one thing: when you're tearing a paper, what are you doing then? If you're tearing the paper, right, when you're tearing the paper, you are actually applying force on this area. And if you see the force is this way, it is parallel to the surface. So to tear a paper, you need to apply shearing stress. So when you are pinching your friend, you're actually applying shearing stress. When you twist the skin, right, you're applying shearing stress there. It's not longitudinal. When you catch your friend ka hand and you pull it, that's your longitudinal stress. But when you catch your friend ka, hand and twist it, it is a longitudinal stress. So there are two kinds of stresses. So when you're doing a construction, right, tell me one thing. So it is more difficult. Is it easy to tear a paper or easy to stretch a paper? It's more easy to tear a paper, right? If you try to stretch a paper, after some time it will just tear open, but it's difficult to stretch. So if you look at paper, paper can withstand longitudinal stress but cannot withstand shearing stress. So every material that when you say strong, it might be weak in some direction, it might be strong in some other way, right? So a paper can withstand longitudinal stress, right? But cannot handle shearing stress. The moment you try to apply force parallel to that, it'll start tearing, right? So it is easy to tear. Did you ever try to open this, dairy milk silka or any plastic cover? Is plastic easy to stretch or easy to tear? Normally, dairy milk and all, right? They give you this, this edges like this, na, so that you can easily tear. But what if you have a cover like this proper, and if you try to tear it from the middle, so what does the plastic do? Plastic is easy to stretch. You can stretch it, but it is difficult to tear. So that means a plastic, right, cannot withstand longitudinal stress, but they can withstand shearing stress. So the materials will have different nature there. So now you tell me, in your building, we have pillars, right? And we have beams. There are two different things, pillars and beams. Can you tell me which one will have longitudinal, which one will have more shearing stress? So in your house, the pillars are these ones, beams are the horizontal ones. if you look at the pillars, right, the entire weight of the building is pushing it down, so they withstand longitudinal stress. But when you look at the beams are placed like this, isn't it? The mg or the entire weight is pushing down, so this is the area. Force is acting like this. The force is acting like this, and this is the cross-sectional area. And if you see the beams also, right, they have a slight, I'm exaggerating the figure, but they do have a bend, they sag. So beams have a lot of shearing stress. So this is the reason next time, if anytime you see construction, observe that. If you have a pillar, let's say they use some amount of steel. When they construct a beam, they use at least 2 to 3 times more steel. So there is a thing there, a concrete is very good in compression. You can put a lot of weight on a concrete and they can really sustain a lot of weight. Know that building Kuala Lumpur mein hai na, that Petronas Twin Towers. That entire building, right, the foundations and all, they used a lot of concrete. The entire building ka weight is around 2 lakh tons. And it is entirely on a platform of concrete. They did use steel, but concrete was more. Simple reason, a concrete is cheaper than steel. 1 kg concrete, you can make it around 3 to 4 rupees when you make it in bulk. A steel will cost you around 300 to 500 rupees per kg. So Petronas Twin Towers, when they started constructing, they had a problem with the budget. Did you ever see Tom and Jerry cartoons? Normally, when they make skyscrapers, first they make a skyscraper with skeleton. This is entirely made of rods. Observe here. The Tom and Jerry are running on top of the rods. So normally when you build a skyscraper, that's what they do. They build the entire structure with rods and then they fill up the gaps. Because if you use steel, right, they can withstand both compression and elongation. They're pretty strong. But concrete can withstand compression. You can put a lot of weight, like steel, it will withstand. But the moment you try to stretch it, concrete will break into pieces. So you should not use concrete any place where you are sure there will be shearing stress. Exactly right, everyone. So whenever there's a shearing stress, you use a lot of steel. It becomes expensive. Now, tell me one thing. You must have seen a building, right? Your house or anything. Look at the pillar of your house and look at the pillars of a metro. Why metro pillars are so thick? Is the weight of the train more than your building or your society of 40 floors? Your 40 floor building ka pillars are actually thinner than the metro ka pillars. So let me ask you this. So metro ka pillars have a problem with longitudinal stress or shearing stress? Metro ka pillars experience what stress? How shearing stress? If you observe, na, dekho, metro ka side view, if you see, this is how they keep it. They have that pillar in the middle, right? Now, think about it. Every time the train goes, how is the friction on the train? Forward. The friction is taking the train forward, right? That means by Newton's third law, that same friction will act on the backward. Now, the train on the other side will go in the opposite direction. The train is going this way and the train is going this way. Both the trains don't go in the same direction. That means this friction will be this way. Sorry, this way. Can you see what is happening? Whenever the trains go left and right, they're producing a frictional force about which there is a torque. That entire section is trying to rotate. The pillar is getting a twisting force. So every time the train goes, the metro pillars are twisted. They're trying to twist. We don't let them twist. And this happens every day. How many times? If the trains are doing, let's say, 400 trips, every pillar is being twisted 400 times per day. And the metro ka lifetime is around 75 years. So you want these pillars to sustain for 70, 80 years, every day twisting it 400, 500 times, right? And that too at a huge force. So these things undergo shearing stress. So that is the reason they're so thick. After building a pillar, they don't stop. For that extra protection, what they do, they actually, better than a circle, right? A cube is even a better form. They seal it with a cubical form. Kabhi dekha, some pillars are, the bottom of the pillar becomes a cube kind of thing, and the upper pillar is a circle kind of thing, cylinder. So they reinforce it. Wherever they know they need more force, they reinforce it. So anyway, so that is a little about that shearing stress and longitudinal stress. Volume stress is same as pressure. So that's really not more. That comes especially when you're trying to compress the overall body. But shearing stress and longitudinal stress, you should know. You must have heard this word, right? I twisted my leg. You will rarely hear, people saying, the leg got fractured or something. Most of the people that twist their leg. That is a shearing stress. Anyway, so that is there. So I'll just write it down again. So it is important when you're dealing with materials. In IIT Madras, now we used to have a professor. He's a chemical engineer. So my roommate, right, he's also chemical. So this guy used to come and tell stories. So this prof, now he worked in a lot of universities, Europe and everywhere. And finally, he retired and came back to India, and he's working in IIT Madras. He is the HOD of Civil Engineering Department. Long back tha, 2007 ka baat tha ye. Getting it? So this guy, na, in his office, na, he used to have a machine. Concrete ka mixer hota hai na, that thing. Right? That machine is there 24 into 7, it is always running, it seems. So this guy comes every day, whatever he feels like, he just dumps into that. One day he will put rubber inside with concrete. One day he will throw pencils and concrete. He will just throw anything into the concrete. And after that mixing for 1 or 2 days, then he takes the material and then tries to do testing. That way, he invented something called rubber concrete. Right? So this rubber concrete, right, you can actually use it in cold countries. Normally, concrete becomes very cold, but this rubber concrete, right, remains warm. So it is especially used for insulation. So in doing all those weird things, now he also discovered something called liquid concrete. So this liquid concrete, right, it flows, right? It flows and it sets off very fast in 5-7 minutes. So it is especially useful. Let's say you have a crack or something like this, a deep hole. Now, if you try to put cement and try to push inside, it doesn't go properly. But if you can put some support here and if you pour liquid concrete inside, it will go and fill up all the gaps, and it, fills up pretty nice. So he tested the material, it was working really well and everything. Then he went to different companies, L&T, this big construction companies, Oberoi and all. And he told them, see, this is the material that I invented. It has so much strength and everyone. So IIT professor, na, so they're like, okay, sir, good and all. But so they entertained him, but still they had a doubt, said, but did you use this in any big construction before? We can't directly use it. So he said, no, I didn't use it anywhere on a big scale because I need an opportunity. So no one gave him an opportunity to use it. He got pissed off. You know what he did? He brought a land in Chennai. He built a 3-floor building, his own house, with liquid concrete. And then when anyone says, "Na, does this material work?" You know what he says? Can you see this house? My wife, my kid, my son, my grandson, all members of my family stay under that house. That I built with liquid concrete. That is the kind of trust I have on my material. And then IIT Madras, they built, the entire stadium ka upper covering, right? They built it with liquid concrete. So I think later on he did get a lot of projects, but that was the thing. So material science, there's a lot of scope, especially in European countries, right? They love material science. So what is the longitudinal stress? So this is a tension perpendicular. So when you say restoring force, remember it is a tension. So tension perpendicular to the cross-sectional area. Be careful, it is not pressure. So if you have a rod like this, if you pull with F and F, so you're pulling here, this is called elongative stress. I hope you remember tension is F. Again, this thing looks like an LN chapter. If you know how to find tension, half the chapter is over. This is elongative longitudinal stress. That's your full name. Same thing, if you're pushing inside, you're trying to compress. This is compressive longitudinal stress. Then we define something called, so first we will talk about longitudinal stress, then we will see shearing stress, then we'll go volume stress. We'll go one at a time. So longitudinal stress is the biggest one. Then we define something called longitudinal strain. So again, understand, in fluid mechanics, what did we do? Instead of using mass, we used density because density is constant for liquids. Instead of using force, we used pressure because force per unit area was more, making more sense. Same way, in elasticity, instead of using force, we use force by area. We call it stress. Instead of using elongation, we use elongation per unit length. You're getting it? So studying per unit length will give you a better idea than studying the whole thing. So longitudinal strain is given by delta L by L. So delta L is the change in length from natural length. L is your natural length. So if you think about it, we're kind of saying force and elongation. That's it. These are the two things. So now when you take a material and you deform them, when a material is deformed up to a limit, the longitudinal stress is proportional to the strain. It is like saying F is proportional to X, F is equal to Kx. The proportionality constant is given by, I'll simply write it as stress. The proportionality constant is given by Y, which is called Young's modulus. So Young's modulus Y is stress by strain. Okay, so this is your main formula there. So it's a constant. It depends on the nature of the material and temperature. The Young's modulus of steel is greater than Young's modulus of copper. Again, obviously, if you increase the temperature, the bond distances will increase and they'll mess up that interaction force between them. Clear with this? Now, there's a name for this thing. This is called Hooke's law. So let me put on the formula there. So this is our first formula here. So Y is equal to stress by strain. What is stress? Tension by area. What is strain? Delta L by L. So we get Y is equal to tension length by A delta L. Right? So for convenience, right, we'll write delta L as elongation. Convenience, we will write. It just looks good, nothing much. I'm used to it. So E is that elongation or compression. There. So this is your final formula there. Y is equal to TL by A. T is the tension. You can copy down this formula. Area of cross section. E is the elongation. For rigid bodies, what will be y? What will be the y ka value for rigid bodies? Y tends to infinity. So what does y tell you exactly? What is the physical meaning of y? Higher the y, more difficult to deform the body, at least longitudinally. So a rigid body can never be deformed, so y ka value will be infinity. So simply y tells you how difficult it is to deform the body along the longitudinal direction. And one more thing, be careful. This formula is valid only when tension is constant. If tension changes, we have to integrate. I'll show you that later on. Clear with this? Let's see a few questions on this. Again, remember what all things I taught you. I taught you only two things. Longitudinal stress is tension by area. Strain is delta L well, and stress by strain is Young's modulus, and this is the formula there, TL by AE. Clear? Let's see the first question. Again, like I said, it's all NLM only, so don't think it's something new. If you know how to find tension, chapter is almost there in your hands. So we got two cylinders. They're placed along the same axis. This cylinder का radius is 2r. This cylinder का radius is r. This length of the cylinder is L. This length of the cylinder is also L. So you can take this point as x is equal to 0, this point as x is equal to L, and this is point as x is equal to 2L. So x is measured from the top. These are solid cylinders. Coaxial, solid, cylinders of density rho. Both have same density. So plot stress versus x graph. Again, remember what is stress? Stress is tension by area. So just to give an idea, say, listen, if I cut it here, the weight of this part will be the tension here. So that tension by area is the stress at this position. If I cut it here, then this entire weight will act on this area. So this entire weight is the weight by area will give you stress. That versus this distance. Are you getting what I'm asking you to draw? I want you to plot tension by area versus x graph. That is stress. Let's get this. So as you come down, you can clearly see the weight is changing and the area also changes. So how will your stress graph look like? Plot stress versus x graph. And this is important. Huh? Did you ever notice? Did you ever see a bus ka wheels? No one actually puts bus ka wheels on the corner. You know why? The middle part, right, will have too much stress. It will actually sag. So if you see the wheels, right, they're actually something like this. Especially if you see this airport ka bus, those wheels are quite different. If you see those buses are longer and they're a little more broad than the regular buses. Let's get this, everyone. Try. I'll give you 2 minutes. Like I said, it is all about finding tension as function of x and dividing by area and plotting a graph. Let's see how you do this. And others do keep your cams on. Hmm. Everyone should try. Should I help you with one part? Take a minute and I'll show you. Up to x is equal to 12. Naresh, man, how did you get constant? You have to be careful with x. Huh? See, remember, x has to be measured always from the top. So let me show you. See, let's say distance x from the top. So we are doing it in two parts, okay? So we are doing this for x between L and 0. Be careful because after L, the area is changing. So we have to split the problem into two parts. So you're taking only till here. That means this shaded area is the weight, tension or normal reaction. So tension will be mg of the shaded area. How much is that? Density, volume is pi r square into x. Agreed? That is the tension. It is changing with x, right? Into g. So what is the stress? Tension by area. Which area? The cross-sectional area, which is pi r square. So that would be rho g x. It's a linear function. Check it out. Are you clear with this? बस इतना ही करना था. Get the tension divided by area. Any doubts on this? Then for the second part, you're taking for x less than 2L but greater than L. Means you have crossed the first cylinder. Means you have gone till here. Now the entire weight will be this plus this. So be careful. X has to be measured always from the top. So the tension will be, what is the weight of that cylinder? Rho into pi r square into L. That is the weight of the upper cylinder. Plus that extra piece, what will be this length? This extra piece will be x minus L. So that will be rho. The cross-sectional area will be pi into 2r whole square into x minus L. That's for the shaded part there. Please check. X has to be measured always from the top because that is how it is given in the question. X coordinate is measured from the top. So therefore, the tension will be rho pi r square Lg plus rho 4 pi r square xg minus rho 4 pi r square Lg. That would be, if you take out rho pi r square g common, you end up with 4x minus 3L. There. You want stress. Stress is tension by area. Which area? The big one. So that is pi 2r whole square. That would be rho g by 4, 4x minus 3L. That would be rho g, x minus 3L by 4. Straight line basically. Yeah, you're done. Now if you try to plot the graph, stress versus x graph. So initially the stress was increasing linearly. Rho gx, it's a line passing through the origin till x is equal to L. There will be a discontinuity there. Rho g X minus 3L by 4. Kind of, because suddenly the area has become 4 times now. So the graph drops and starts from here. There. So there is a discontinuity in the graph. So this value will be a rho GL and this value will be a rho GL by 4. This will go until x is equal to 12. Please check. It is just two straight lines with a discontinuity in the middle. Any doubts on this? Clear? What did we use actually, right? Elasticity, because we just said stress by area. Other than that, there is nothing new there. Any doubts on this? Please ask me. You should know how to calculate tension and a graph. Any doubts on this? Let's see one more. Let's see one more like this. We have a rod here. You are pushing with F and you're pushing back from F. Mass M, length L. So this is x is equal to 0 and this is x is equal to L. This is on a smooth floor. Plot stress versus x graph. Remember, rod will not remain at rest. You're pushing, both the sides you're pushing. There, let's get this. Again, like I said, it's all about finding tensions. You got an interesting graph. You guys forgot how to find tension. I taught you how to do this in laws of motion and finding tensions. Remember these questions? Find tension in the rod at a distance x from the right. So how to do these kind of questions? Find the acceleration. Wherever you want to find tension, cut it there. You'll get two pieces. Take any one piece, draw the FBD, get the tension. Hope you guys remember this process. We did all this stuff in NLM. So what to do? Step one, get the acceleration here. This is F. This is also F. So acceleration is 2F by m. So at a distance x from here, you want to find tension. So cut it there. Wherever you want to find tension, cut it. Choose any one piece. I will choose the right part. Then the forces will be F and the tension T. Acceleration A. This part will be m, whose mass will be total mass by total length into x. F minus tension is equal to small m into acceleration. F minus tension is equal to mx by L, and to acceleration is 2F by m. That will give you tension is equal to F into 1 minus 2x by L. And stress will be tension by area. That's it. And we just have to divide by area and elasticity is done. That is F by A 1 minus 2x by L. So if you actually look at the graph, This thing is interesting. So when x is 0, the stress is actually positive. It actually goes into a negative territory. So why is that happening? So what's actually happening is the front part of the rod, if you actually look at the front part of the rod is getting elongated. The tension, the rod is being stretched. This is an elongative stress. That's the meaning of a negative sign. The stress has gone from elongated to compression. The left part of the rod is being compressed. This is a compressive stress. Think about it. Let's say your friends want you to go somewhere and you're not ready to go. So what do your friends do? There is one guy who's catching your hand and pulling you, so your right hand is getting stretched, and there is one guy who's pushing you from the back, so your back is getting compressed, isn't it? You actually experience both the stresses, longitudinal compressive and elongator stress. So in this case, the rod, right, the front part is getting compressed and the back part is getting compressed and the front part is getting elongated. Clear with this? Got this? Any doubts on this? So this exactly happens at the center of the rod. Ah, yeah.
Sir, in rigid bodies, we used to have an assumption that the pseudo force acts on the COM. Will it hold
Okay.
true here?
Ah, but your centromas itself will shift.
Yeah, I mean, I
We
think
neglect
that.
actually, see in all these problems now, we neglect that elongation. It is actually too small. The Young's modulus value is in the range of 10 power 10. So the elongation will come in the range of micrometers, millimeters. For a 1 meter rod, it might compress around 0.01 mm, millimeters. So we neglect the change in center of mass. But if you consider that, what
Okay,
you're
sir.
saying is true. मतलब ये scenario में the center of mass would have shifted, greater than L by 2,
Okay, sir.
right? And not only that, na, if you say center of mass, then the problem becomes what? Because of the compression, the density of the rod is changing. It will become too complex. We'll not get into all that. And the changes are too small. So let's do something like this. More. Let's say we have a rod.
So it's mostly not possible to solve in pseudo frames, right?
Uh, so we have 3F here. We have F, and we have F. So someone is pulling in the middle of the rod. So we have a rod with four forces. Pi is the Young's modulus, A is the area of cross section. Find the elongation in the rod. Again, remember the formula. How to find elongation? This is the formula you have to use. Young's modulus is equal to tension, length, area, elongation. So if you know how to find tension, just put it in the formula, you get E ka value. That's what I said. If you know how to find tension, half your job is done. Let's get this. Okay, we have one answer. Did you guys get the tension? That's the first thing you have to do. The rod does not have same tension everywhere. So how do you find that? Same story. Wherever you want to find the tension, cut it. Just don't cut it at the intersections. Huh? They'll be undefined. So what is the acceleration? The whole thing is at rest. 3f, f will cancel. So if you cut it here, the tension will be 3f. If you cut it here, 3f minus 2f, the tension will be 2f. If you cut it here, the tension will be f. So the three rods have three different tensions. So let the elongation be E1, elongation be E2, elongation be E3. So you can treat them as three separate rods. What is the formula? Young's modulus is equal to tension length by A into elongation. So E will be tension length by AY. So you're done. So E1 will be tension, which is FL by AY. E2 will be 2FL by AY. So each rod will have different elongation, 3FL by AY. Therefore, the total elongation will be 6FL by AY. Easy? Yeah, right, Aditya. Right, Utsav. There. So if you see the rod, each section will have different tension. Clear with this? Clear, na, Srihari? Pratyasha? Vedika? Clear? Let's see one more. This is the standard model, right? This is a good one. So let's say we have a string which is tied between two walls. Negligible mass. We have a wire of negligible mass. Young's modulus Y, area of cross section A, length L. All three things are there. Then what you did, you attached a mass M in the middle. You took a mass and you attached mass M. And because of this, the wire started sagging in the middle. Now I exaggerated the figure. इतना नहीं होता है, it's very small. So this distance here is x. A mass m is attached at the center and it goes down by x. Right? Assume x is much smaller than L. So you can use binomial approximations. Find x. So we got a wire between two walls. It is massless, so initially it remains flat. So once you attach some mass, it in the middle you get a triangle like this. If x is very small, find x. Again, when I say very small, compared to the length. Let's get this. It's an important question. It's a good one. Again, remember, what is the formula? There's only one formula you have. Y is equal to TL by AE. This is the only formula I taught you. This could be a good integer question. There are some really good questions based on this and, thermal expansion. That will be the next chapter. We'll be doing it there. Near area. You'll get a cube root. Hmm, so this is your y shape. So let's take this to be theta. Theta is very small. This will be x. This will be L by 2, right? And be careful. This length is how much? This is x square plus L square by 4. So what is the elongation here? The elongation will be 2 times root over x square plus L square by 4 minus L. Isn't that the length of the thing? The new length is this, the V shape. That's your elongation, final length minus this. So from here you can take out that L common there. That would be L by 2. Then that would be 1 plus 4x square by L square whole power half minus L. 2 2 will cancel L. I can use binomial approximation. Hope you guys remember binomial approximation. 1 plus x whole power n can be approximated to 1 plus nx. You can do this only when x is much less than 1. Here x is much less than L, so that x by L is very small. This will be L 1 plus half into 4x square by L square minus 1. 1 1 goes off and you end up with 2x square by L. This is your elongation. And you attach the block M here, so this will give you tension T and this will give you tension T. And this angle will be 90 minus theta, so that would be 2T cos 90 minus theta is equal to mg. That would be 2T sine theta is equal to mg. Again, since x is small, theta is small, the telling you now the thing is not tough, but the approximations you have to be clear. Sine theta becomes approximately tan theta, and tan theta becomes x by L by 2, which is 2x by L. Therefore, your tension becomes mg by 2 sine theta.
Sir, we can also use r theta as our.
कर सकते हो वो भी. Then that would be 2 into 2x by L. So tension will be mgl by 4x. There, I got my main two ingredients. I needed the elongation and I needed the tension. Then once I got this, you're done. So take this and dump it in the formula. Y is equal to tension length by AE. Y tension is how much? mgl by 4x. What is the elongation? A 2x square by L. Bring all x to one side, you get x cube. mg L cube by 8ay. Therefore, x is equal to mg by 8ay whole power 1 by 3l. Have a look at the equations. You get a cube root there. Right, Utsa. Right, Aditya. All got this? Any doubts on this? Let's see one more. We have a hollow shell with a very small thickness, like a coconut. R is the radius, T is the thickness. Focus everyone. And R is much, much greater than T. So it's a very thin shell. You can ignore it. Outside is vacuum. Then you started pushing air inside, and the pressure is P. You're pumping more and more gas inside, right? B is the braking stress. What is braking stress? Again, the maximum stress a metal can withstand before it cracks. And this thing does not depend on the area and all. It depends on the nature of the material and independent of area. Max stress material can withstand. So if you apply this much stress, it is going to crack. So B is, again, it is stress means force per unit area. B is independent of area and depends on nature of material. Find the maximum pressure of the gas so that the shell does not crack. So if you keep on pumping the gas inside, at some point the whole thing will crack. What is the maximum pressure of the gas so that the shell does not crack? There, let's finish off last one for the day. Try, try. Everyone should try. How do you start? Again, like I keep saying, you just need to find the tension. So how do you find the tension for this? Draw FBD of the half shell. Remember what is longitudinal stress? It is tension perpendicular to the area. If you draw FBD of the half shell, we have done something like this in the excess pressure in a soap drop, soap bubble, the liquid drop. The shell would look like this. Able to visualize? The gas is pushing inside Since the pressure is constant, I can use projected area, which is pressure of the gas into pi r square. And who's stopping this? This cross section. The tension on this cross section is actually connecting this left and the right shell. The tension will be acting like this, just like surface tension. The tension is acting on this cross section. You're done. So what is the tension? Tension is pressure into pi r square. What is the stress then? Stress is tension by area. Which area? The area where the tension is acting. That is tension by area, which is 2 pi r into thickness, small t. That is the shaded area. So it's acting on the circumference with a thin thickness, right? And this should be equal to B because that's the maximum stress you can have. You're done. So P into pi r square. There, if you know the projected area in this thing, it's so we'll get P from here. 2B T by R. That's your maximum pressure. Anything more than this, the shell will crack. Clear with this? Right, Samya. All clear with this. I hope you're getting it right. If you see, again, we are just drawing FBDs and FBDs. There's nothing there. Once you got, you have to put in the formula. And if you see today, right, we did all constant forces. So next class when we catch up, we will be doing even variable forces where you have to integrate and all that stuff. We'll also introduce something called elastic energy. So if there's a force, there is always an energy sitting there. So yeah. Okay, with that we'll wrap up for that day. And surface tension is done. So please make sure to go through the notes and solve, solve your material. I'll be also sending you a sheet on viscosity and surface tension today or tomorrow morning, Max. So you can try that because I think the questions are all scattered for viscosity and surface tension. They're not at one proper place. I'll send you some material